Now we'll discuss that is the next topic, that is C looping structures. Now here again we'll be considering the same data packet checksum routine example, and we'll analyze how actually the compiler will treat the increment loop, okay, where the loop counter we are going to increment in each iteration, and how actually the decrement loop is efficient compared to the increment loop we are going to analyze. Okay, with respect to the loops, this is what we are going to discuss, whether to choose increment loop or decrement loop. Okay, and other thing is whether what condition you have to consider with respect to the loop counter. So if it were to be either a signed or unsigned loop counter, a specific condition you can make use of in case of a decrement loop. So what is that condition which you can use? How actually it improves the efficiency or the performance that we are going to see. And in some situation, we can say that do while loop is better, it performs better compared to the for loop. So what is that situation? That with an example we'll be seeing. Okay, and finally the last concept in under loop structure we are going to discuss is unrolling, loop unrolling. So what actually we mean by loop unrolling, that with example we are going to discuss. Okay, so let us start see looping structure. So first we'll see loops with fixed number of iterations. So that means if I say 64, that means 64 times the loop will be executed. So the number of iterations is fixed. It is not variable. Okay. So that we are going to discuss. So let me start. And we are considering the same example, that is the data packet checksum routine, and we'll see how actually the compiler will treat the looping. Okay. That is the increment loop, how it is treated by the compiler, and what will be the compiler output generated. So that we are going to analyze here. So it is the same routine that we have already discussed in the previous classes. Okay, see the return type of the function is int, name of the function it is checksum, and this is the argument the function receives, int star data, where it is a pointer to the array. Okay, within the routine you can see it is the for loop, which is an increment loop we are finding here, and the statement that is repeated 64 times is sum plus equals star data plus plus. So just observe what kind of loop we are considering here for fixed number of iterations. It is increment loop. Okay, so first what we are discussing is whether to go for increment loop or decrement loop. So that we are trying to check out, and whether which type of loop will be efficient, that we are going to analyze here with the compiler output. Okay, so in this increment loop, we are seeing where the loop control variable is incremented in each time. So initial value of the loop control variable is 0. We are testing it with 64, and it is updated in each iteration. So what will be the compiler output for this? This also we have already discussed. So no change at all. It is the same code what we had discussed in the compiler output. So you can see here, since the pointer itself is incremented, it is LDR instruction that is used to access to different locations in the array or different elements in the array. And you can see here add instruction is used. You can observe for updating the loop control variable, and compare instruction is required for testing the condition whether the value has reached 64, and conditional branch instruction is used here, that is BCC, for deciding whether to go for the next iteration or not. So these are the three instructions what we can say that is implemented or that is used for implementing this for loop structure. Okay, so how many instructions the compiler output has taken for implementing this for loop, which is an increment loop. That is what we have to analyze with this example. We have taken a data packet checksum routine which is having increment loop, okay, for fixed number of iterations. Just note, it is for fixed number of iterations and increment loop considered. So for this, what is the compiler output here seeing? So it is three instructions taken for implementing the for loop structure. So what are those three instructions that are used for implementing the for loop structure? One, it is an add instruction, that is to increment the loop control variable. See, add r1 comma r1 comma hash 1 is given. So it is for incrementing the loop control variable. And another instruction for comparing the value with 64. So and a compare instruction is used for checking whether I value is less than 64 or not. And one more instruction is used for implementing the for loop structure, that is conditional branch instruction. So to continue the loop if I is less than 64. So branch CC, it is a conditional branch instruction that is used if the first operand value after comparison, if the first operand value is smaller than the second operand value, you know that carry flag status will be 0. If carry flag status is 0 means it is successful, that is execution of BCC instruction, where the control will be transferred to the label wherever that is checksum underscore v5 underscore loop is given. So for the next iteration, the control will be transferred to. So these are the 3 instructions that are used to implement for loop, which is an increment loop. Okay. But what you have to notice, so using 3 instructions for implementing the for loop is not efficient. So this is what you have to note. Then how actually we can overcome this on ARM architecture. So you can just implement the loop using just 2 instructions. So which are those 2 instructions which you can use to implement the loop in ARM architecture? So these are the 2 instructions. A subtract instruction you can write for decrementing the loop counter. You know that SUBS instruction, if you use, it is going to affect the condition code flags. Okay, and then you can use a conditional branch instruction to decide whether to repeat the loop or not. Say for example, once the result of subtraction becomes 0, in that case Z flag status gets set. You can just repeat the loop, branch not equal, be any instruction you can use, you can repeat the loop. If 0 flag status is 0, you can go for the next iteration. Once 0 flag gets set to 1, you can just stop the iterations. So with only 2 instructions, you can implement that is the looping construct. So that is what the efficiency you can find here. If you are going for increment loop, it is going to take 3 instructions to implement the for loop structure. But if you are going for a decrement loop, the same for loop where the counter is decremented in each iteration. So if you are going for such construct, in that case, it is going to take only 2 instructions. Okay, so the number of instructions are reduced. So that's what you're going to see under this topic, that is loop counter. So what are the 2 forms of having the loop counter? Either you can go for an increment loop or a decrement loop. So if you are going for increment loop, then it is going to take 3 instructions for implementing the for loop structure. So but it is efficient for going for decrement loop, where the loop counter will count down to 0 rather than counting up. Okay, so that's what we are seeing here. And you can also see it is the data packet checksum routine, the same routine whatever you saw in the previous slide, but the increment loop has been replaced with decrement loop. See, for I equals to 64, I not equal to 0, I minus minus. Earlier it was I equal to 0, I less than 64, I plus plus. Now the increment loop has been changed to decrement loop, so that the number of instructions in the compiler output is reduced, which improves the efficiency. Okay, so that is what you are seeing in this example, the improvement if we are switching to decrement loop rather than an increment loop. And it doesn't affect the data access from the array here. You are updating the pointer itself. So what for you are using the loop control variable in this example? It is just to decide the number of iterations. So whether you use increment loop or decrement loop, the expression what you are repeating within the loop, it is not affected, right? So here that is one more advantage. If you are going for indexing method, so in that case the increment loop, if you are using, you know how actually I will be varying, and if you are using decrement loop, how actually I is going to vary. So but here since it is pointer itself updated in each iteration, whether you are using increment or decrement, that doesn't affect the array access. Okay. The most important thing you have to note with respect to the loop counter is, if you are going for increment loop, the number of instructions taken is 3, okay, to implement the for loop structure. But if you just replace that increment loop with a decrement loop, then it is going to take only 2 instructions. So on ARM architecture, with 2 instructions, you can implement the that is for loop structure. Just see the compiler output. You can just check here in this. Just 2 instructions are used. Which are those 2 instructions? SUBS R1 comma R1 comma #1. The counter is decremented here. Then a branch instruction. Here, which branch instruction is used? It is BNE instruction. So once R1 takes the value 0, 0 flag gets set to 1. At that point, the loop is going to get terminated. See, rest of the statements are same. If you just compare the previous version compiler output with this, it is the same code, but only changes. Increment loop has been replaced with decrement loop. Rest of the statements are same. So accessing the array, since pointer itself is updated, it is the post index method that is used to access the array element. The element accessed is in R3 register here. Once LDR instruction is executed, R3 is having the data that is fetched from the array. Then the counter is decremented using SUBS instruction, which affects the flag, that is condition flags. Then add instruction is executed to sum up the data that is retrieved from the array. The data will be held in the R0 register. R3 is having the data fetched from the array. R0 initial sum is 0. Once it is added, it will get the result in R0. And we are testing the 0 flag status. If 0 flag status is 0, that means we have not completed all the iterations. Control will go to the beginning of the loop. See, the process is repeated. And what you can observe here, it is just 2 instructions that are used to implement the loop. Okay, see, the SUBS and BNE instructions are implementing the loop here. And in this checksum example, you can see how many instructions per loop is executed. It is just 4 instructions. Which are those 4 instructions, which are called as loop instructions here? LDR instruction, SUBS instruction, add instruction, and BNE instruction. So these are the 4 instructions that are repeated in each iteration. Right? This is much better than 6 instructions for checksum underscore v1 and 8 instructions for checksum underscore v3. If you just recall the previous versions, what we have discussed, the number of loop instructions executed are more. If you are going for decrement loop here, it takes only 4 instructions per loop here. For this example, what we have considered. And only 2 instructions we have used to implement the for loop, which is a decrement. Okay, so this is one important concept you need to note here. See, these are the 2 major topics you have to go through in this chapter, efficient C programming. One is C data types and the other one is C looping structures. Okay, and each topic is most important. So it is loop counter, what we have discussed just now, where instead of going for increment loop, better to go for decrement loop, where for increment loop, it takes 3 instructions for implementation, whereas here in a decrement loop case, just 2 instructions, that is SUBS and a conditional branch instruction, say BNE. Only these 2 instructions are used for implementing the loop. Okay. So for this example, that is the data packet checksum routine, it has just 4 loop instructions used, which are repeated in each iteration. Right? So this is about the loop counter. Now we shall move on to the next topic, that is signed and unsigned loop counter. So whether you take the loop counter as of signed data type or of unsigned data type, so what is the condition you have to use in common for a decrement loop? So that's what we are going to discuss here. So for unsigned loop counter, say I, okay, we can use either of the loop that is continuation condition. So that means for deciding about the next iteration, what is the terminating condition you will be usually writing in the decrement loop. So you can either write I greater than 0 or I not equal to 0. So here we are considering an unsigned loop counter, say I, okay. So for testing the terminating condition, either I can write the condition as I not equal to 0 or I greater than 0. So since it is unsigned loop counter variable we are taking, that is if the value cannot be negative. So any condition you write out of these 2, it is fine. It works fine and it will be efficient. Okay. Whereas in case of signed loop counter, so if you're going for signed loop counter, so in that case, if you use the condition I greater than 0, okay, as the test condition, in that case, what is the output compiler is going to generate? So just see, we are seeing only that loop implementation compiler output here. Assume this is the loop header you have given for I equals to 64, I greater than 0, I minus minus, where I is a signed loop counter. So if that is the case, where I is a signed loop counter, so what is the compiler output that will be generated? See, this is what the compiler output generated, which takes 3 instructions. So if you are going for unsigned loop counter, any of the two conditions can be written, and in that case compiler is going to generate only two instructions for implementing that loop for unsigned loop counter. Whereas if you are going for signed loop counter, see, these are the three instructions compiler is going to generate with I greater than 0. So if you are testing the condition for the signed loop counter with I greater than 0, okay, so then these are the three instructions it is going to take. And one more drawback with this is, see, first let us analyze this code, and then we shall see what is the problem with this condition I greater than 0 for signed loop counter. Okay, see, sub r1 comma r1 comma hash 1. So first the counter is decremented, then we are comparing the value of r1, that is the loop counter value, with 0. Since it is signed counter, we are using BGT, branch greater than. So if the value is greater than 0, then control will come to the beginning of the loop, wherever the loop is defined. So this is incomplete compiler output you are seeing. So what we are concentrating on is the loop implementation. Decrement loop implementation, where the loop counter is declared as of signed data type. Okay, so that's what we are concentrating on. If it were to be signed data type, so these are the three instructions compiler is going to insert. So sub r1 comma r1 comma hash 1 to decrement the counter. Then compare instruction is used for comparing the r1 value with 0, and then branch greater than instruction, conditional branch instruction is used. If it is satisfied, then control is go to the beginning of the loop. So what if I value is say minus 0x 8 followed by 70? If this is the I value, you can see how actually these three statements are getting executed. I is decremented first and then it is compared with 0. So what will be the value once I is decremented? If this is the value in I and once it is decremented, so the value it takes is 0x7 followed by 7f's, which is actually greater than 0. So that means once you compare that 0x7 followed by 7 zeros, 7f's with 0, it is greater. The value is greater than 0. So since it is greater, condition is satisfied, control will go to the beginning of the loop wherever it is defined. So infinitely the loop will be repeated. Okay. So to avoid this, so what is to be noted is, so you need to go for the terminating condition I not equal to 0 for whether it is an signed loop counter or an unsigned loop counter. So this is going to say one instruction over the condition I greater than 0 for signed I. So if you are going for signed loop counter, if you had used I greater than 0 as the test condition, then it would have taken 3 instructions for implementing the loop. Okay. But if you are using the test condition as I not equal to 0, whether it is signed or unsigned loop counter, need not worry. But the test condition, if you use it as I not equal to 0, in that case, one instruction it will be saving. So what is that instruction? So just subs instruction can be executed, and branch not equal to instruction can be executed. Since I not equal to 0 you are testing, so any instruction can be executed. So only two instructions can be used to implement the decrement loop. Okay, whether it is signed or unsigned loop counter, that doesn't matter. So this is what you need to note with respect to this topic, that is signed and unsigned loop counter. So whether you go for signed loop counter or unsigned loop counter, what will be the condition which you have to use? It is I not equal to 0, which is going to say one instruction over the condition I greater than 0. That is for the case of assigned data type for the loop counter variable. Okay, so this is what you need to note. So this is about signed and unsigned loop counter. So far we have seen two concepts with respect to C looping structures. One is better to go for, that is, decrement loop compared to the increment loop, which saves the instructions. In case of increment loop, 3 instructions were used for implementing the loop, whereas if you are going for decrement loop, just 2 instructions are sufficient. Similarly, If you are going for the test condition in the decrement loop, as I not equal to 0, it takes only 2 instructions for implementing the loop. Whereas if you are going for I greater than 0, and if the loop counter is of signed data type, then it is going to take 3 instructions for loop implementation. So which is more efficient? That is the condition. Which condition is more efficient in case of decrement loop? It is I not equal to 0 rather than using I greater than 0. So this is what you have to note. Now moving on to the next topic. So that is C loop with variable number of iterations. So we have seen fixed number of iterations within the loop. Now we shall see variable number of iterations in case of the loop. Okay. So that means variable number of iterations means you are reading the n value. The example what we have considered is data packet checksum routine, and we have assumed that there are 64 words in the array. Those 64 words are to be added. It is fixed number of iterations. But here what we are discussing is the same data packet checksum routine, but the packet is of arbitrary size. Okay, if I say 10, 10 words we have to add. So we are also passing the n value as argument to the function. Okay, so that's what we are seeing here. So we want our checksum routine to handle packets of arbitrary size. We pass that in the variable n, giving the number of words in the data packet. Okay, so this is checksum version 7 example, which shows how the compiler handles the for loop with variable number of iterations. So what is the topic we are discussing? C loop with variable number of iterations. So the same data packet checksum routine is considered here. See, in checksum underscore v7, this is the function name, and observe 2 arguments are passed here. That is the base address of the array and the n value, which indicates the number of words in the data packet. And we are taking the variable sum. This is the decrement loop we have considered, and just observe what type of loop we have used here. It is for loop. Decrement loop for loop where we have used, and this is the same expression within the for loop. Sum plus equals star of data plus plus, and return sum finally. So for this, what is the compiler output generated? Just see here. So what you have to observe in this compiler output is, in case of decrement loop, okay, the for loop is the loop we have used, which is an entry control loop. Just see, it is an entry control loop what we are using, and also it is variable number of iterations we have considered. So in this case, what you have to notice, the compiler is checking the n value, whether it is non-zero. Okay, so at the beginning of the function, this is what it is going to check. Compare R1 with 0. So R2 is a variable which holds the sum in each iteration. That is what been allocated. This is the register that is being allocated to hold the sum in each iteration. That is R2 register. R1, it is having the n value. Okay, and R0 is a register which is holding the address, base address of the array. Just see the order in which the arguments are passed: data and n. So for data, which register is used? It is R0 register, which acts as a pointer to the array. And n, for that which register is allocated, it is R1 register. And to hold the sum, it is R2 register that is allocated. So how actually the registers are being allocated, you can analyze here. Okay, R0, R1, R2 are the registers that are being used in this compiler output. R0 for the base address of the array, R1 for n value, and R2 for holding the sum. So here at the beginning of this routine, compiler is comparing the value of R1 with 0. So that means whether there are any words in the array. That's what is being tested. If n value is 0, then control will be transferred to the label wherever end is defined. Okay, it goes for returning the sum to the calling function. Sum to which register it will be passed? It is to R0 register. I told the return value will be normally passed through R0 register. Okay, the R2 value which is having the sum, that register content is copied to R0 and control is transferred to the calling function. So this is what the additional part you are seeing. If you are going for decrement loop, that too in specific we are dealing about for loop. For loop, if you are using for variable number of iterations, this is what you have to note. Okay, so in that case, compiler will check for n value whether it is non-zero on the entry to the function, but it is not required. So if you are dealing with array, means usually array will not be empty, so no need of testing the condition for 0. Okay, whether there are no entries in the array, so that condition need not be tested. So in such situation, okay, where at least one time the loop has to be executed, then do while loop will give a better performance, okay, compared to that is for loop. So that's what you are seeing. We will be replacing this decrement loop, which is implemented using for. The same decrement loop we are going to replace using do while loop, which improves the efficiency. Okay, reduces the code size and it improves the efficiency. Okay, and it improves the code density. So that's what we are seeing here. In the next version, usage of do while loop, for which case variable number of iterations. So kindly note, this is what we are discussing. It is loops with variable number of iterations. It is the same data packet checksum routine we have considered, but here we have replaced a for loop with do while loop. See, do within a pair of flower brace, it is the instruction sum plus equals star data plus plus that is being executed, and after that close the do loop, and this is the while loop written, while minus minus n not equal to 0. Okay, this is the decrement loop for which is implemented using do while loop. Okay, so what you can observe in the compiler output, see at the entry to the function, it is not testing for 0 here. The rest of the statements are same. Okay, 4 instructions are the loop instructions that are repeated. It is same as the previous compiler output only, no change at all. Okay, R0 is used as a pointer to the array. R1 is having that is the index value, and R2 which hold to hold the sum. All statements are same. Only change you are seeing compared to the previous compiler output is it has removed this entry, that is the condition testing. See, whatever I have highlighted here in red line. So these two statements are being removed if you are going for do while loop. Compiler will not test whether the n value is 0. Okay, that condition has been removed. These two statements are being removed in this compiler output. So that's what you can notice here. Okay. So it is actually saving of 2 cycles. So in this compared to checksum underscore v7, here you are seeing 2 cycles savings here, which improves the performance. Okay, so this is about selection of do while loop, yeah, for loop for variable number of iterations. So which is more efficient or which performs better in case of variable number of iterations? It is do while loop. So since it compiler will not check for 0 here. Okay, at the entry of the function, and it is going to save here 2 cycles. So this is about the C loop structure with respect to variable number of iterations. So the last topic in the C looping structure, it is loop unrolling. So first we'll see what loop unrolling is and how actually this loop unrolling can be done with an example we'll be discussing. So we have already discussed decrement loop in the previous topics, okay, where what is the number of instructions used for implementing the loop. So it is actually 2 instructions in addition to the body of the loop. So within which are all the loop instructions, you may be writing some instructions for repeating in each iteration. In addition to that, to control the loop, there will be loop instructions written which will be repeated each time when loop is executed. So that means in the decrement loop example what we have discussed, the loop, how it is implemented using 2 instructions, subs instruction and bne instruction, which costed 2 instructions in addition to the body of the loop. So what is the body of the loop operation to be performed? Say if you consider the data packet checksum routine example itself, it is the retrieving the data using LDR instruction. We have to retrieve the data from the array and that has to be added. Okay, we need to compute the sum of all the elements in the array. Performing addition operation and retrieving the data from the array. These are the two instructions which are to be repeated in each iteration. In addition to this body of the loop instructions, we are having two more instructions to be executed for implementing the loop. Okay, so which are those two instructions? Subtract to decrement the loop counter and the conditional branch instruction. So these two instructions we call as loop overhead. So we have to repeat actually just LDR and add instruction, but to control the loop we are using two more instructions, SUBS and BNE instruction. So these two instructions are called as the loop overhead. Okay, but here what you have to note is on ARM7 or ARM9 processors, subtract instruction takes just one cycle, but branch instruction takes 3 cycles. So since two instructions are to be repeated in each iteration, so what is the overhead per loop? It is 4 cycles. So it gives overhead of 4 cycles per loop. Yes or no? So since two instructions in addition to LDR and add are to be executed to control the loop, how many cycles those instructions are taking? SUBS takes 1 cycle and branch instruction takes 3 cycles. So in total, it is 4 cycles overhead per loop. Correct. So how actually we can save these cycles? It is through the concept, it is loop unrolling. So what do you mean by unrolling a loop? So it is nothing but repeating the loop, okay, that is the loop instructions, whatever you have written, several times. And in proportion to that, you are going to reduce the number of loop iterations. Okay, so that is called as loop unrolling. Repeating the loop body several times and reducing the number of loop iterations by the same proportion, that is called as loop unrolling. So that with an example, we shall see. So it is the same data packet checksum routine we are discussing where the loop is unrolled 4 times. Okay. Now how many words are to be added? It is say for example, say 64 words you want to add. In that case, just see how actually this loop unrolling works. It is do while loop that is used. Okay. And see in the previous data packet checksum routines, only one time this summation statement was written. Sum plus equals star of data plus plus. But here, how many times we have unrolled this loop instruction? It is 4 times. Since 4 times we have unrolled, accordingly, we have updated the loop counter variable as n minus equals 4. So 4 times you are decrementing the loop. Okay. So this is what you have to note here. See, in this case, this is an example for loop unrolling. Loop unrolling means repeating the loop instruction several times, and in proportion to that, the loop counter has to be updated. So it is reduced. Number of iterations is reduced here. N minus equals 4. Since already 4 times, one time the loop is executed, 4 elements in the array are accessed. So the counter has to be decremented by 4 here. N minus equals 4. So this is what the instruction we are going to write. And if you assume n value as 64, okay, are you getting? If you take n value as 64, so how many times the loop has to be executed?
16.
16 times. See, so just see one time when you execute the loop, decrement loop, if you are using in that case the overhead, loop overhead, I am talking with respect to loop overhead. So it is 4 cycles. Per loop, it is 4 cycles. We are trying to reduce that loop overhead by saving some cycles. So how to achieve that? We are going for loop unrolling concept where the loop instructions are repeated several times. Accordingly, in proportion to that, we are reducing the number of iterations. So in this case, see only 16 times the loop is repeated. Okay, this reduces the number of iterations. By what amount the loop overhead is reduced? You can see here. So with this loop unrolling, we have reduced the loop overhead from 4n cycles to 4n by 4, that is n cycles. Only to n cycles, the loop overhead is reduced. Say if you had repeated 64 times, if you take n value as 64, 64 times if you had repeated the loop, per loop, the overhead is 4 cycles, 64 into 4. It is, I think, 256. 256 cycle overhead you had if you had not unrolled. Okay. So since we have unrolled here, So how many cycles it has taken? It is just 64 cycles. 16 times the loop is repeated. So one repetition of the loop, overhead costs us 4 cycles. What is 16 into 4? It is 64. Compared to 256 cycles of overhead, here you are seeing only 64 cycles of overhead, loop overhead. See, we are able to save some cycles with this unrolling concept. So this is the meaning of loop unrolling. Repeating the loop instruction and in proportion to that, reducing the number of iterations. It is called as loop unrolling. And you can see the compiler output generated here. See, only there is 4 pairs of LDR and add instructions. We are seeing simple. LDR, see R3 comma content of R0 comma hash 4. Counter is decremented by what amount? It is by 4. Okay. After that, add instruction to add the data that is retrieved from the array. Again LDR, then add instruction to add the data. LDR, add instruction to add the data. And again here LDR and add instruction to add the data. The BNE instruction. After SUBS instruction, at the end you can see after all 4 additions are completed, BNE instruction is executed to decide whether to repeat the loop or not. So finally, once the loop terminates, once Z flag gets set to 1, control comes outside the loop where R2, which holds the sum, final sum, that is transferred to R0 register and control is returned to the calling function. So here we are trying to reduce the loop overhead. Okay, if you are going for that is unrolling the loop, in that case we can save some cycles. So in this example, if you assume n value as 64, in that case here it is 16 times the loop is repeated. 16 into 4 will cost 64 cycles of loop overhead, compared to if you are not unrolling this, it was taking 256 cycles of overhead. Okay, so this is what you have to notice here. So now moving on to a few questions with respect to unrolling the loop, okay, which we have to address. These are the 2 questions which you need to ask whenever you are going for unrolling the loop. So how many times you should unroll the loop? This is one question. And what if the number of loop iterations is not multiple of the unroll amount? So for example, what if n value is not multiple of 4? In the example, what I considered for n, I had taken 64, where 4 times you are repeating, that is 4 times you are unrolling the loop instruction. So 16 times the loop will be repeated. So 64, it is multiple of 4. You easily you unrolled 4 times and you did it. So what if n is not multiple of 4? Okay, in that case, what we have to do? So we shall try to answer these questions. So to start with the first question, you should not go for unrolling all the loop instructions. That is, if you are having multiple loops in the program, you should not go for unrolling each of the loop instructions for several times. So this will result in increased code size and the performance will be reduced. So when you'll go for unrolling the loop, so if it is most important code which affects the overall performance of the application, only such loops we have to unroll. Okay, this is one thing. And coming to the second question, what if n is not multiple of 4? In that case, you have to arrange. So one possibility is you have to see that array size are multiples of the unroll amount. If it is not possible, then you have to add extra code. You have to write one more loop to take care of those leftover cases. So for example, you want to repeat the loop, say 67 times. Are you getting? 67 times you want to repeat the loop. So you can go for loop unrolling concept, where 64 times you can repeat. That is, you can consider 64 as the number of words to be added, and where you are going to unroll 4 times. Okay, the loop instruction. So 16 times the loop will be executed to handle those 3 words which are leftover cases. For that, you can write a separate loop to add the left 3 words. Okay, how actually that is done, we'll see here. That will actually increase, but as I told, you should not go for unrolling each instructions, the loops, whatever you have implemented. Only the important one which is affecting the overall performance, only such loops we have to unroll. And usually in multiples of 4 2, 4, 8 we can unroll. Okay, and accordingly the iterations will be reduced. So just see the example where the n value is not multiple of that is 4. Just see here. Here we are not discussing the compiler output for this. We are trying to just see how actually two loops are being used. One loop for handling that is the n value, which is multiple of 4, and another for handling the leftover cases. Okay, just see. This is int checksum version 10. These are the two arguments passed, the pointer to the array and the n value, and initial sum is 0. Just see the for loop. For I equals to n divided by 4, I not equal to 0, I minus minus. And another for loop we are using for I, and how many times the loop is unrolled here? It is 4 times. So 4 times. Okay. And you can see for I equals to n and 3. See, bitwise AND operation is performed here for handling the leftover cases. I not equal to 0, I minus minus. Okay, and one time that is the only once we have written the sum plus equals star data plus plus. This will be repeated for leftover times. So just see, if I had taken 67, if the n value is 67, then I equals 67 by 4. What it results in? What will be the quotient? N is equal to 67 by 4 means? What is the
16.
quotient? 16, right? So that means how many words we are able to add? If n is equal to 67, number of words in the data packet were to be 67. Okay, with this first for loop, how many words we are able to add using this loop unrolling concept? 64 words. Which are the, sorry, how many words are left out to be added?
3.
It is just 3 words, right? So I is equal to n and 3. We are taking least significant 3 bits and we are masking higher order values here in that n. So we will be left with only 3. If you perform AND operation, you will be left with only 3. I is initialized with 3. 3 not equal to 0. That is I minus minus operation is performed, where 3 times this sum plus equals star data plus plus is executed. Okay, this is how we can just do the or we can handle the case where n is not the multiple of the unroll amount. Here the unroll amount is 4 and the n value is 67. So since n is not multiple of this unroll amount, how actually we are able to handle it? We can just have this these two for loops. One for loop for that is the for handling the number of words, which is multiple of 4. That is the unroll amount, and another loop for handling the leftover case. Okay, this is what you have to know, and you cannot use do while loop here. Okay, see, that's what I've given as note here. Both n by 4 and n and 3, these two expressions, they can be 0. So that's why do while loop cannot be used. So do while loop when we'll use, if at least one time the loop is to be executed, the body of the loop is to be executed, then only we'll go for do while loop. But since in this case I equals n by 4, the expressions we are using is n divided by 4 and n and 4, bitwise and 3. Since these two expression values can be 0, we cannot make use of do while loop for this loop unrolling concept where n value is not multiple of the unroll amount. Okay, so this is what we need to note. So this completes loop unrolling. We saw what actually loop unrolling is. Okay, what is the use of loop unrolling? We need to, or we are trying to save the loop overhead, number of cycles we are trying to save by just repeating the loop instructions for several times, and accordingly we are going to reduce the iterations in proportion to that. Okay, so this completes loop structures, C loop structures. Okay, so we shall just summarize whatever we discussed with respect to loops. See, use loops that counts down to 0. So that means you need to go for decrement loop rather than increment loop, which performs better. So then the compiler doesn't need to allocate a register to hold the termination value and compare that with 0 is free. Additional register allocation is not used here if you are going for decrement loop. We can compare that. Increment loop was using 3 instructions. Decrement loop is can use just 2 instructions. Since SUBS instruction will affect the flag, you can just use BNE, conditional branch instruction. You need not write compare instruction to compare a register to check with a 0. So that is not required. Comparison with 0, that instruction is free here if you are going for decrement loop, correct? So then one more point, use unsigned loop counter by default. Okay, usually you need to go for unsigned loop counter, even though if you use signed loop counter also fine, but what is the condition? Continuation condition you have to use. It is I not equal to 0 rather than using I greater than 0. Okay, this is another point you have to note with respect to loops. So next, use do while loops rather than for loop when you know the loop will iterate at least once. So you saw that variable number of iterations we had considered as an example, where the data packet checksum routine we saw, where instead of using for loop, do while loop usage is better, which reduces the instructions, right? Next, it is coming to the unrolling the loop. Unroll important loops to reduce the loop overhead. Do not over unroll. So that means unnecessary loops which are not affecting the performance. Such loops you need not go for unrolling, which reduces the efficiency or the performance. So only you have to unroll the important loops which is affecting or which is having overall effect on the performance. Okay. And one last thing, you have to try to arrange the numbers in the array such that they are multiples of 4 or 8. Okay, for that you can easily unroll, that is by 2, 4 or 8 times without worrying about leftover array elements. So since you need, if it were to be the n value which is not multiple of the loop unroll amount, in that case you may have to write additional loop to handle the leftover cases, which increases the code size and reduces the performance. So you have to try to arrange the array elements in such a way that they are multiples of 4 or 8, so that you can unroll the loops easily by 2, 4 or 8 times, okay, without worrying about this leftover array elements. So these are the points you have to remember with respect to loops. Okay, whether to go for increment or decrement loop, whenever you're using the loop counter data type, if it were to be signed or unsigned, doesn't matter, make use of I not equal to 0 as the test condition. Do while loop you have to use for variable number of iterations compared to for loop. Unrolling is going to reduce the loop overhead. Okay, so this completes loops. So move on to the next topic, that is register allocation. How actually the processor is going to allocate the registers if the number of variables used in a function are more than where the memory will be, where the variables will be allocated with the memory. All those things we are discussing. As I told, from now on we'll be discussing only theory aspects. So this completes the major 2 topics, that is efficient C data types and C looping structures. The C code and the corresponding assembly code we have analyzed for these 2 major topics, and you can expect any type of question on these 2 major topics. You may be asked to explain with the C code as well as assembly code that particular concept, or you may be asked to write the assembly code given with the C code. So such questions you can expect along with explanation of the concepts. Okay, coming to the register allocation. See, the compiler attempts to allocate a processor register to each of the local variable what you are using in the C function, and it can use the same register for different local variables if the variables doesn't overlap. So if the variables are not getting overlapped in your program, in that case same register may be reused by the compiler. Okay. So, and now we'll see what actually you mean by spilled variable or swapped out variable. So when there are more local variables than the available registers, okay, if too many local variables you are using in your function and more, that is which is more than the available registers, then compiler cannot allocate the registers for holding those variable values. That excess variables for that processor stack will be used. Okay, such variables for which the memory is allocated in stack. So they are called as spilled variables or swapped out variables since they are written out to the memory. Okay? You may be asked to explain what actually mean by spilled variable or swapped out variable. So when there are more local variables than the available registers, then compiler will store those excess variables on the processor stack. So such variables for which memory is allocated in the stack, they are called as spilled or swapped out variables. Okay. And if you want to implement the function efficiently, so in that case, you have to minimize the number of spilled variables. So don't go for unnecessarily taking additional variables. Okay, you need to reduce. So the important point you have to note here, you have to try to limit the number of local variables in the loop to 12. If it were to be less than 12, in that case, for each of the variable, the registers can be allocated. If it is exceeding that, in that case, it has to go for allocating for the variables, the stack memory. Okay. So if the compiler doesn't need to swap out the variables, then it chooses which variable to swap out. If it does need to swap out the variables, then it is going to choose the variables to swap out based on the frequency of use. That means if a compiler comes across the situation where the variables has to be allocated in the processor stack, in that case, which variable it is going to choose, it depends on the frequency of use. So some variables are more infrequently used, or some variables are most frequently used. Based on that, it is going to allocate the registers for the variables, and rest variables for which memory will be allocated in the processor stack. Okay. And as I already mentioned, try to limit the number of local variables in the internal loop, that is within a particular function, to 12. So compiler should be able to allocate the memory for these variables in the register, okay, in the ARM register. So this is about register allocation. Hope you have followed. Is this clear? This completes register allocation. With respect to register allocation, what you have to notice, you have to minimize the number of spilled variables. What actually mean by spilled or swapped out variables? If the number of local variables within a function are more than the available register, then compiler is going to allocate memory for them in the processor stack. So what you have to do, if you want to implement a function efficiently, what you have to notice, you have to try to limit the number of local variables in the loop of the function to 12. So that compiler can allocate for all these variables ARM registers. So this is what you have to note. Okay. Is this clear? So we completed C loop structures and register allocation. Have you all followed?
Yes, ma'am.
Okay.